Good morning, students. Today we'll start on an interesting topic, gravitation. All of you know the name of the planets in our solar system. You just see how the planets revolve around the sun. I think all of you know the names of the planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Now, all of you know that Pluto is not a planet, it becomes a white dwarf. So all these 8 planets in the solar system, they revolve around the sun. All of you know in the planet in the elliptical orbits. So regarding the motion of this planet around the sun, you have 3 laws given by Kepler. So Kepler's laws of planetary motion. First law, that is called law of orbits, or you can say the law of ellipses. Just the path of the planets around the sun is elliptical in shape, with the center of the sun being located at one focus. Or you can state in different way also, all the planets revolve around the sun in elliptical orbits, having the sun at one of the foci. You know, students, in a circle there is one center, but in an ellipse there are two focus. When the planets revolve around the sun is situated at one of the focus. You just see here the sun is, right? It is one focus, and this point X, this is another focus. So in these elliptical orbits, when the planet revolves, there are two focus, right? The sun is situated at one of the focus. Clear, students? So you just remember this statement. All the planets revolve around the sun in elliptical orbits, having the sun at one of the foci. This is very important. This elliptical orbits, see, this is elliptical orbits, right? And the sun is at one of the foci. Clear? So then the second law is, you can say that the law of area or areal velocity, right? You see, when the planets revolve around the sun, see, when the planet revolves around the sun in elliptical orbit, right? Suppose the time taken from P1 to P2 is same as the time taken from P3 to P4. For example, suppose from P1 to P2, it takes 100 days, right? And from P3 to P4, if it is same 100 days, then the area shapes out by its radius vector. This area, you see area A1, I have marked area A1, and this area A2, they must be equal, right? So when the radius vector drawn from the sun to the planet sweeps out equal area in equal interval of time. This is very important, right? Equal area in equal interval of time. You see, equal area in equal interval of time. Area will be same only when the time taken from P1 to P2 is same as the time taken from P3 to P4, right? So we can state in this way also. An imaginary line drawn from the center of the sun to the center of the planet will sweep out equal area in equal interval of time. Or you can say this statement also, the radius vector drawn from the sun to the planet sweeps out equal area in equal interval of time. If see, students, if it sweeps out equal area in equal interval of time, that means the area divided by time is constant during planetary motion. For any planet, when it revolves around the sun, the areal velocity, that means area divided by time, is always constant, right? In rotational motion or in revolutionary motion, one parameter angular momentum is also constant or conserved. Here, you have seen the areal velocity during planetary motion is always constant. Areal velocity means area divided by time. Since the planet makes or sweeps out equal area in equal interval of time, its aerial velocity, area divided by time, is constant. Sometimes the question is coming, what is the dimensional formula for aerial velocity? Aerial velocity means area divided by time. Area is L2 divided by T. So you can say L2 T to the power minus 1, aerial velocity, right? So during planetary motion, this aerial velocity is always constant. Clear, students? Next you come to the third law of Kepler, that is, you can say, law of time period. That is important. First law is law of orbit. Second law is law of area. Third law is law of time period. Or in some books it is also written law of harmonies. Harmonies law, right? You see, here we are talking about the revolution of the planet around the sun, right? Another concept is there, rotation of a planet about its own axis. But the motion of the planetary motion means that the revolution of the planet around the sun. When the planet revolves around the sun, right, the square of the time period, as this time period for our earth is 365 days, 6 hours, right? Revolution of the planet around the sun. One time period is 365 days, 6 hours for our earth. Similarly, different for different planet. Rotation of the planet about its own axis. For our earth, you know that is 1 day, 24 hours, right? Here we are talking about the time period for a revolution of the planet around the sun. The square of this time period, you see, the square of this time period is directly proportional to cube of its semi-major axis. You see, semi-major axis, I have seen this is the semi-major axis, right? From the sun with this focus, right? You know this is an elliptical orbit, so this is the aphelion, this is the perihelion. When the planet revolves around this sun, this is your semi-major axis, and this line is your semi-minor axis, right? The square of this time period is proportional to the cube of its semi-major axis, right? The square of the time period is proportional to cube of its T square proportional to a cube, right? Suppose there are two planets revolving around the sun. First planet time period is T1 and for the second planet is T2. Then we can write T1 square divided by T2 square, right? T1 square by T2 square, T1 square, right? You just see it is T1 square by T2 square, T1 square by T2 square is equal to how much then? Tell me, T1 square by T2 square equal to A1 divided by A1, or in some books it is written A2, A1 by A2, right? A1 by A2 is whole to the power 3, we can write, because some problem also coming, short question is coming. Suppose two planets are at distances 10 to the power 13 meter and another is at 10 to the power 12 meter, then what will be the ratio between the time period? You can put this formula, T1 square by T2 square equal to A1 by A2 cube, right? So square of the time period is directly proportional to cube of its semi-major axis. This is law of time period, or you can say law of harmonies. So three laws you should remember, very interesting. First law, that is law of orbit, right? The planets revolve around the sun in elliptical orbits and the sun is situated at one of its poles. Second law, that is law of area, or you can say aerial velocity. When the planet revolves around the sun, its radius vector sweeps out equal area in equal interval of time. Or you can say during planetary motion, the aerial velocity remains constant. Very interesting. The aerial velocity remains constant, right? Next you come to Laplace law, you come to Newton's law of gravitation. All of you already acquainted this law in your school level also, right? Everybody you know in the universe attracts every other body. So that force of attraction, you can say that is gravitational force, right? Any particle of matter or any body in the universe. It may be the between two planets. It may be between sun and a planet. It may be between the planet and the satellite. Right? Whatever may be the body, whatever may be their masses. Right? This force of attraction, this gravitational force of attraction, is directly proportional to the product of their masses, right, and inversely proportional to the square of the distance between them. You just see there are two bodies I have taken, whatever may be the bodies. One is of mass say m1, another is a mass m2, right? This force I am repeatedly telling, this is the gravitational force. There are so many forces between two bodies. Maybe gravitational forces, electrostatic forces between two charged bodies, nuclear forces between any two constitutory elements of the nucleus, right? Here we am talking about the gravitational force. Any body, any bodies, maybe there is a force of attraction. That force is gravitational force I am telling. This gravitational force is directly proportional to product of their masses, you see, and inversely proportional to the square of the distance between them. So F proportional to m1, m2, proportional to 1 by r square. If I will combine these two, then it will be F proportional to m1, m2 by r square, or we can write F equal to G m1, m2 by r square. This is very important, students. F equal to G m1, m2 by r square, right? So this G, capital G I have written, it is a proportionality constant known as universal gravitational constant. Why I am telling universal gravitational constant? Because this value of G, capital G, gravitational constant, is same everywhere in the universe. This value is same for Earth, or Jupiter, for Mars, or you can say at the center of Earth, at the top of a hill, right? At the equator, at the wherever you go, the value of this G, capital G, gravitational constant, is same everywhere in the universe. That's why it is known as universal gravitational constant, right? This value G, you should also remember this value G equal to 6.67 into 10 to the power minus 11 Newton meter square per kg square. 6.67 into 10 to the power minus 11. You just see, because G, we can write G equal to F r square by m1 m2. F r square means F Newton meter square by m1 m2, so kg square. From this formula only I am writing the unit and dimension, all this Newton meter square per kg square. So this is the unit of gravitational constant, and its value for every places, it is 6.67 into 10 to the power minus 11 Newton meter square per kg square. But in the next lecture, we'll come across small g, about small g. This small g is different for different places. So the weight of a body is different for different places. This value different for different planets, different for different places of a planet. But here I am talking about the gravitational constant, capital G, that is same everywhere in the universe. That's why it is known as universal gravitational constant, right? So this formula you should remember, F equal to G m1 m2 by r square, and this force, this formula is true for any two bodies in the universe. You just mark here the distance between the center I have taken, because this force is also applicable for very massive body, right? For example, say this is the force of attraction between sun and earth, say. That's why this distance should be taken from their centers, right? Suppose this first body is exerting force F1 on second body, and the second body is exerting force F2 on the first body. But these two forces, F1 and F2, they must be same, just like action and reaction. They are equal in magnitude and opposite direction, right? The force on M1 is same as that force on M2. These two forces must be same. F1 equal to F2, and that must be equal to G M1 M2 by R square, because in both the cases the force is between the two bodies, right? That's why the product of the two masses should be taken. F1 equal to F2 equal to G M1 M2 by R square, right? You cannot say for F1 it will be no M2, for F2 there is no F1. That's why these two forces, F1 and F2, the force acting on two bodies are equal and opposite to each other, like action reaction pair, right? Sometimes why I've written this thing, because sometimes one can ask you, suppose there are two bodies, one is of 50 kg and another is of 100 kg at a distance of say 2 meter. What will be the ratio between the forces acting on them? The ratio is always 1 is to 1. The ratio is always 1 is to 1. Clear, students? Because these two forces are always equal, right? Whatever may be their value, this ratio, you see, F1 equal to F2 equal to G M1 M2 by R square, right? So very easy to remember. The gravitational force of attraction, or you can say any particular matter in the universe, attracts any other body with a force directly proportional to the product of their masses and inversely as the square of the distance between them, or you can say the distance between their centers, right? So in the next lecture, we'll come to small g, right? How this small g, acceleration due to gravity, vary with altitude, depth, right? And with the latitude, all those things we will discuss in the next class. Today, thank you, students. I hope you will enjoy this lecture because this is a very interesting topic of this gravitation. Thank you all.